Hello, welcome. Thank you everyone for coming. So today we'll be doing the reverse engineering class. We're in a different room and it's a bit of a smaller crowd, I guess, because a lot of people are having the graduation ceremonies today, but it's a good thing we will have the video. So also hello internet, hello online people. I hope there's more of you present at the moment. So, reverse engineering, the one where we dig deep into the rabbit hole. Big thanks to everyone who participated in creating of this class, especially Maria. She's in Seattle now, but she's watching us, and Sebastian is also in Argentina, but they are here in spirit, I'm sure, and then they'll be back soon again. And thanks to rest of the team, the audio team and the design team. So this is the standard class links, documents, matrix, audio, etc. So we start as usual with the survey from the last class. It was very nice class, and for majority of people it was all right. It was maybe a bit too fast for some people, but it depends again on your the prerequisites you have and the knowledge you have. But it's good that it was nice for the majority of people. So we also had some feedback. One I think was from the people online that the class required some knowledge of programming that wasn't taught before. The thing is that this is at our university and faculty, this is a master's course, so students usually come here with some knowledge of at least elementary C programming and stuff. So there are some prerequisites for the course written in the website, but we will see in the future what we can do to make it more, I guess, easier to follow for other people. There were some architecture issues, but that's due to Mac. I think we warned that at the beginning of the lecture, just that the architecture makes certain exploits we were doing last time harder to do. For the students here, there were no issues because they were doing it in the Dockers that had the same architecture. And somebody said that in the CTFD system, the past homeworks are not visible. That's true. We said that the homeworks would close on the November 7th. There's still no option in CTFD to just have the possibility to see the homeworks and not interact with them. So once they are closed, they are hidden from view, and that's it. But if you wanna, it's a free software. If you wanna implement a feature for that, you can try it. It would be much appreciated, I think, by a lot of people. Okay, so that was the introduction. Yeah, there are also no Pioneer prizes this week because there was no assignment last week, but there will be assignment for the next week, so the prizes will be back again. But we have these prizes here for the people participating today and talking with us, interacting, so should be fun. So just briefly the class outline for today. We will do some intro of what is reverse engineering. We will remind ourselves of some stuff, mainly the assembly, x64 architecture, and GDB debugger, and then we will do two very fun reversing exercises. The first one is gonna be where we reverse a network protocol, and then we're gonna reverse an actual binary, which would be a binary bomb, and that will, I guess, take most of our time today because it has multiple stages, but we'll get to that one. So before we start, this part is for the online students because it's gonna take some time to get your Docker started and stuff. Please go start the class 9 Dockers now, and once it starts, to be able to follow this class, you will need to SSH to this IP and use the pass admin, and then you should be able to follow and do all the exercises like we present them here. Okay? Are we okay online? Do people hear us?
Yeah. So is this working? No?
Yeah.
Yes? No?
I
Okay.
think so.
Okay, if you can hear me. There are some issues with the URL link of the live streaming on the Strato Cyberlab. We are fixing, so it should be up shortly.
Oh, okay, thank you. So, reverse engineering, first part, to learn a little bit theoretically. We won't do much theory today, it will mostly be hands-on stuff, but just the beginning to give some introduction. So, has anyone here done any reverse engineering whatsoever at some point in their lives? Anyone? No one? Okay, Martin, San, Andra, yeah, nice. And have you used maybe some reverse engineered applications or games, or you're not torrenting, cracking? Okay. Nice people here. Okay, so reverse engineering is basically when process of analyzing a black box system to understand how it works, how it operates, how it functions. Basically, you don't have insight into the code, you just know how it runs, and you're trying to figure out exactly what it does. If you figure it out well and deep enough, you could even be able to reconstruct the code, but that's... And for example, you know, there are a lot of people who are cracking games. They are basically reverse engineering them to try to figure out how to generate the, you know, access key so that you don't have to pay for some game if you want to play. But since we are here an ethical hacking class, we won't talk about that stuff. But how the cybersecurity experts actually use reverse engineering, it's used, and it's very useful and helpful to us as analysts to analyze malware, to see how it behaves, because you know, you get a new malware, you don't know, a lot of computers is infected, and you need to act fast to stop it, but you don't know how to stop it because you don't know how it works. So you have to figure out how it works, and then if you're good enough or lucky enough, because there's a lot of luck that goes into reverse engineering and experience, you'll be able to stop malware. But we'll see that later. So in some standard engineering process, we first design the code, then we code it, we compile, we fix bugs, then we compile again, then we fix bugs again, we do some testing, we fix more bugs, we assemble it, we add new features all the time, and you know, at some point the code goes into the production and it's running there, we are fixing if something happens. But in reverse engineering process, we are kind of doing it the other way around. But a lot of these steps are not there, like fixing bugs. That's not a job of reverse engineer. You're not, I mean, unless you want to fix some app because it annoys you how bad it is, but it's, I mean, people do that. So first you would start by disassembling the code and looking at the machine code, basically the assembly. Then you would, if you're able to, try to decompile it to see the decompiled version, some C-like code or something. Of course, there are often some obfuscations or anti-debugging methods that so you can't look at the decompiled version, so you just look at the disassembly, and then you think and think and think, and then cry a bit, and eventually you figure out what happens, and you reversed the application. You either stopped the malware or you cracked some application, found the key or something. So, as I mentioned already, there are many use cases. We want to understand how malicious software operates, how is it spread, what are its goals and capabilities, does it have some vulnerabilities or weaknesses. We also want to fingerprint and identify threat actors, and again, it helps us then develop countermeasures against malware, etc. So, just a little bit of motivation, because from this point on we're gonna go to practical stuff. As I said, there won't be much theory. So there was a famous malware 2017, WannaCry, and it spread, actually it was a, it had some ransomware and worm components, so it could spread, you know, from one computer to another, and it spread really fast, like in just a few hours, like 150 countries were infected, over 300,000 computers. So initially, as it's natural, everybody was a bit scared, and then, you know, reverse engineers got to their jobs, and they started analyzing it. They didn't know what to expect, and like this is a good example how you might get lucky sometimes in reverse engineering, because as they were doing that initial read through of the disassembly, they noticed there's some URL there they were curious what it is. They checked the domain and they saw it wasn't registered. So they said, okay, let's see what happens if you register it. You know, when you do this like try around, find out stuff, it can sometimes hit you on the head. But in this case, it was a good idea because this domain was actually a kill switch. So once it gets registered, all the bots, all the infected computers are shut off. So by looking at the disassembly and just trying to see what will happen if they register a domain, they managed to stop a very serious virus. Again, it was a kind of a silly thing, but it worked. So yeah, this is just also to give you an...
Anyone remembers? Wanna cry? Like, anyone? Yeah? Wow, I see some hands.
Some people,
Do you still cry at nights?
Nah, they solved it quickly. We didn't worry
So
anymore.
it was a huge thing, right? And as Mori said, it was key. In this case, it was key the reverse engineer work, because without them, this wouldn't have happened. It wouldn't have been stopped, right? And it cost millions of dollars in destruction, like billions actually. So it was really, really important, and not only the reverse engineering work, but actually understanding what it is and like the whole context. So it was like super nice.
And this also shows you that sometimes, even though you are a professional, you can't know everything. You have to make some guesses and test some hypotheses, and then okay, maybe they're right, maybe they're wrong. If they're wrong, you try again, because we will be doing later some stuff, and it might seem to you like I'm just, how does he know this? It's so random, and yeah, it often is random. But after like 50 attempts, you find the thing that works, and you figure out what's going on. But of course, due to the time reasons of the how much we have for this class, I won't be able like to test every hypothesis. But yeah, in practice, it can take really some time to analyze application, especially if there is some serious malware that has some obfuscations, because they don't want you to analyze it easily. Or even like the game companies, they put a bunch of obfuscations into their code so that people don't crack them too fast, and then, you know, that you can play some expensive games for free really fast. I mean, there's usually some rule that it needs to hold out at least 3 to 6 months, because that's when the company makes the most revenue. So the every protection for reverse engineering is going to be broken at some point, but sometimes it's going to take a year, sometimes it's going to take 10 minutes, and you want it to hold out as much as possible. So yeah, the last bits of this theoretical part, how we can analyze software we know nothing about. There's static analysis. That's if we can analyze file without actually executing it. We just get the disassembly of the file, but it's almost impossible when you have the packed malware, because you're not getting the real disassembly. You first have to unpack it and then look at the disassembly code. But on the other hand, since it's not run, it's really safe for your systems, for the analyst and stuff, you know. But the other way is, of course, the dynamic analysis, where you literally run the program, try stuff out, and try to figure out what it does, how it works. But in the case of malware, it's not really recommended to run it in your systems. You need some sandbox or something, so it's a bit more dangerous. But on the other hand, you can use debuggers and similar tools to understand the code better. Of course, the best situation, and what is mostly used in reverse engineering, is the combination of static and dynamic analysis. Because from the dynamic analysis, you can't always figure out everything, so you need to look a bit at the code, try to understand it, see what it does. So there are many tools to do reversing, and a lot of these tools are really expensive because they are, you know, industry tools. They, especially these disassemblers and the compilers like IDA we will be using today. The other famous one is Ghidra, which is based on Java. We have some Binary Ninja, Hopper, also other like non-disassembly tools, like some debuggers or decompilers are useful. We're gonna be using GDB as well today. Also, just looking at the type of file, like Linux commands, you know, file, strings, etc., can be useful in analyzing the file. And there's a Flare VM, which is a Windows tool. It's a pretty solid one I guess. But mostly, one of the most common used ones, I would say, is IDA, not the free version we will be using today, but there's a professional IDA which is really, really expensive, but you get your money's worth if you're a professional reverse engineer. And then probably your company pays for it, not you. So, okay, so I think we can start with the hands-on part. Are you ready, warmed up, present? Okay. So, due to some feedback from the previous years, students were telling us that they would like to kind of see a bit of more of GDB and assembly before we move into the reversing stuff. So we're just gonna refresh our memory a bit, or if you haven't encountered this, you know, this will be your like good introduction to it, and then we're gonna start reversing stuff. So the first part of this is to remind ourselves of some stuff that Martin was talking about last week, mostly registers, some calling conventions, etc. You can all, I've linked you here two very nice cheat sheets for the registers if you ever need to remind yourself for something. And yeah, this is the what we'll mostly be using and encountering while we do reverse engineering today, but in general. So since we are working with 64-bit architecture, we'll mostly see these in our disassembly registered as RAX, RBX, etc. But it's possible that we will see that sometimes we won't need 64 bits to represent something, so we will encounter these EAXs, EBXs. A very common one is this DEL, and we will be seeing it later, which is just an 8-bit version of the EDX or RDX. So, does anyone, okay, it says here, but some of the most important ones are like the RSP, the stack pointer. We had a lot of fun with it last week, so we'll see if it's useful again this week. RAX, also an interesting one, it's a return value register. A lot of return values will be stored there and then passed from the function and stuff. So another important thing to remember about registers, RBP, RBX, and these registers, so are from 12 to 15, they are non-volatile, which means they need to be preserved, and they are preserved by the callee. So because later when we analyze some functions, you will see that the value is just passed from one register to another. It's not changed in any way or anything. That's to preserve the values of the registers, because we have to take care of that in these, or the function does have to take care of that for these registers. The rest are volatile. You can do whatever you want with them. And yes, RDI, RSI, RDX, RCX, and R8 and R9, these 6 are used to pass the 6 integers or pointer parameters to called functions, basically as arguments. If you have more, then it just goes to the stack. So how might the assembly that we're gonna see soon look like, and just briefly how to read it? Usually the standard we're doing now is we have the source and the destination here, so we are moving the data from RDX register to RAX register. The LEA command, also an often one that you will encounter, basically moves the address, this one, to the RDI register. There's this standard operation of addition or subtraction, basically RDX, and is added onto the RAX, and it's stored in the RAX register. We can push the contents from RAX to the stack by growing it by 8 bytes, you know, with the push commands, or the reverse operation, which is pop. And another very common command is jump to an address and then execute whatever is at that address. And there are many variations of jump command, like jump if equal, jump if not equal, the standard jump, and so on. So in your Dockers, you should have Jeff installed, but in case it doesn't work for you for some reason, there are still commands here that you can run to execute. Online people as well, it should be in the Cyber Lab. So just if you want to check if everything is all right, there's a command here so you can try. And now we're gonna start with a simple example. So I'm gonna come back to this. So there's a very simple and very stupid C code, and you can find it here. So you can copy it to your root folder. So if you do this from your root folder, then this is the command to copy. And here there will be all the examples for all the there will be all the codes and the things you will need for all the examples we will be doing today. So just get the entire directory where it's handy for you to use. And we're gonna go to the hello world one, just a simple one to refresh our memory of debugging. And there's a hello world C code there, and we can compile it, and I will go briefly through the code. I mean, it's silly, it's just to show something in the GDB. Basically, it starts with setting the integer variable to 5, and then it checks if this contents of the A is equal to the whatever return 5 function returns, which is 5, but there are some, you know, there's a loop and stuff just so that you can see how it looks when it's disassembled, and that's it. And yeah, when if they are equal, and they should be equal because this returns 5 and this is 5, then we get the hello world. I mean, you can even try to run it if you don't trust me. So hello world, and yeah, it says some number 5 in this case because that's the value of A here. So let's open it in GDB so that we can see how it looks before we go into the real reversing stuff that's gonna be more difficult, and then people see GDB and like, what's this now? So we're here. Is everybody here? So far I hope there shouldn't be any issues. So we can put a breakpoint at the main function, and you can just type B, you don't have to write breakpoint or break or anything, and just the name of the function, or you can, if you know the address, you can do that as well. And I guess we can run the code and look at the disassembly as well. So we run the code, we are here in the main function, we did some we are at this command, you see the arrow here at the moment. There was what we call a function prologue before, where we put the RBP pointer on stack and then move the values. Again, the opposite thing is the epilogue, where we pop the RBP from the stack, and that's kind of what happens at the beginning and the end of function. And then in the middle is the stuff we analyze, but it's a good idea to know how to recognize prologue and the epilogue so that you then don't waste time on it, though it's, you know, very simple stuff. So yeah, we can also what might come handy for us later is to use look at the entire disassembly. So you can just type disass, and you're gonna see the disassembly and where we are now. So we have here command, or we are at the line subtract RSP OX10. Does anyone know what it means? What are we doing there? There's some candy, and there's some dinosaurs and Pikachu, and yeah. So RSP is which register? Do you remember? It was 2 minutes ago. Stack pointer, yeah. And this 10 is the hex value of what is this? Well, it's in hex, but basically we are here allocating space for the arguments, you know, of the function. So that's kind of usually how the functions start. So yeah, then we can, for example, do ni or next I to do the next instruction, and we see we are now here on the mov 5 to this location here. This is basically this part where we are writing 5 into our variable a. Okay, so it's literally step by step. But what I need you to notice here is that after this function there is a call to some other after this line there is a call to some other function which is called return 5. So we can put a breakpoint there as well if we want to for some reason examine that function. Of course, again, this is just a very plastic example, nothing's really happening here, but this just to show you how we will move later to a more complex tasks. So you're not lost there, you can follow. So for example, you can put the breakpoint by doing star and then this address at which the function is. And now we have the breakpoint too. If you want to see which breakpoints you have, you can just do info breakpoints. See, if you don't need that breakpoint for some reason or you made a mistake, you can just do delete and you've removed the breakpoint.
Okay, so in case some people in the internet is catching up, so remember that we installed Jeff and then we copy the reversing class folder, we compile the hello world code, and then we open it with GDB, okay? And now we are looking into the code in there. So
yes.
Yeah?
This
Everyone here is working for you? Yes,
yeah.
No.
Yeah, this is more just to get a hang of how to move through GDB. Basically like a GDB tutorial, we're still not reversing anything that's about to come. Okay. For example, what's interesting here, we have some comparison here, and then based on this comparison, see we are comparing what's in the EAX register, and that's RAX, but the 32 bits. We are comparing it to the RBP minus 4, so there's something here written. And EAX is the, I told you, the 32 bits of RAX. And do you remember what the RAX register is for? What this EAX will contain now here? What will be the value? Take a look at what is the line before this comparison, and you can check what the RAX does, or what kind of register that is. Do we have the thinking music? Okay, so yeah, again, RAX is the return value register. So here we will, in EAX, we will have the return value from this return 5 function. So here there should be 5. We will check it later. So we are comparing 5 to whatever we written here in the at the beginning of the before the function call, and it was also 5. So these should be the same. And then the jump says jump if not equal. So if not equal, if the values are different, the jump will take us somewhere. Here they are equal, so the jump should not happen. It would move. It should continue normally to execute. But let's say that. For some reason, while we are reversing or something, we want to change the address of certain register because we want to test a hypothesis or something. So let's see how we can do that. We can do check X or X, and then it should be RBP. So we know what is written now there. We have the address of the pointer or the register, and the current value. Current value is 0 because still nothing has executed. You see, because we still haven't done this command. So if we wanna do it, we do next instruction. It will do the next instruction. It's gonna, okay, the next one is, so it's the value here should now be 5 because the previous command executed. So it stopped at the return 5 function call. We're not gonna go into the function. No need, nothing special going on there. So we can just do next instruction. And we've come to our comparison. And let's say we want this jump to happen. The situation as it is now, it won't happen because the values are the same. So let's change the value at this RBP register where it's pointing. So we can use the command set and get the address from this command and change the value to some other. So if we type this, okay, the value is still 5, and this is the address where we need to change the value. So set, don't forget the star to reference it, because otherwise you won't be able to change it. And let's change it to 6 or something. So if we check again the value of our register, it's 6 now. So did you all manage to change the value here? So if we do the NY NI instruction, it's gonna say, okay, jump is going to be taken, and then there's some reason stuff. So if we do continue, because we don't want to go line by line. Okay, it ended, and it didn't write the message hello world 5 because the message is only written if they are equal. Very silly example, but just to get a hang of GDB. And when later you see this stuff, this XW, I don't know, breakpoints, what is NI, so that you're not confused at the moment, because you'll be thinking about much more about some other stuff than about this. So, are we okay? What is the time? Perfect. Okay, I'm gonna give you, like, because of online people, 10 more seconds, 20 for everyone to get on the same page. And while you're waiting, if you haven't done it already, you can download this pickup file from here. Both CTU students and online students get it on your device. We're gonna open it in Wireshark on your device, but we'll also need you later to do something in your Dockers. But for now, just get it on your laptop, and you can open it in Wireshark. Because now we're actually gonna start reversing some stuff. Yes. So while you're doing it, I will tell you something about this pickup. So this is a packet capture between a rat malware that's running on some Android phone and the command control server, which is controlling it and sending it some controls, instructions, commands, and the name. If you don't know what rats are, they're remote access trojans. Basically, type of malware. It controls your system through a remote network, and it's typically installed without victim's knowledge. You know, there's some like stuff like TeamViewer, but they are okay. This is like without your knowledge, somebody, or you install it by clicking on some link, but you don't know that you installed it, and somebody can control your device. So this was a project, I think, of one of the students in the Stratosphere for the thesis, and now we have a lot of nice traffic here that we're gonna analyze, capture some packets, and see how we can reverse the network protocol. So do we all have the Wireshark open? Yeah. So in some standard situation you would analyze it more thoroughly, but we know that the communication is happening on the TCP port, on the TCP, so we don't have to look for it now, but in real life it might not be the situation. You would maybe have to go try to figure out what protocol is used for the communication. But now, just to save some time because we have a lot of work, we're gonna just go straight to the TCP and see what we can find there. Okay, so we're there. We have some packets. We have SYN, then it goes SYNAC, then AC, and this is networking 101. Come on, SYN, SYNAC, then AC. Three-way handshake. Nice, thank you. So the communication is established. We've shook hands, and now we can start doing stuff. So let's direct our attention to the first packet that actually contains some data. You see this push here. That means that, okay, some data was pushed. So we can see that we have some data. It's 119 bytes. And when we mark it, it's this highlighted part. Do you tell me if I need to increase the maybe a bit so you can see. So this is some data. We have no idea what it is. We see some 2.2, then 9.1, and then some stuff. Also, if you look at the hex here, there is also, you can see this 2.2, then a blank space, then 9.1, then again blank, and then there's this interesting 1F8B, but then it repeats again 1F8B. What might this be? We don't know, so we have to make some assumptions. That's how reversing works. But before we get to 1F8B, what is this 2291? The 22 plus 91 is 113, but we know that our data has 119 bytes, so it's close enough. Maybe it's a worthwhile path to go there. Does anybody have some ideas? Or no? Basically, let's, since it's kind of really close, let's maybe stick to that idea and to see maybe it's some kind of a header that tells us how much data there's after. Because also if you look at this, there's 1, 2, 3, 4, 5, 6, and 113 plus 6 is 119. So then the complete data package would make sense. So this tells us there's 22 bytes, and then there's 91.
I have a question from the internet. Why is 1F8B interesting?
We will come to that very soon. Like we're just approaching that one. As I was saying, 2291. So maybe there's a 22 bytes, then 91 again. If you look at it and you can count it, it should match here. But let's do it slowly. So we're gonna need CyberChef to kind of reverse some stuff here. So we've found some data. We have some hypothesis that we want to test what these numbers might represent. We still don't know what 1F8B is, but we want to figure that out. We find it interesting because it's repeating twice really soon, so it looks kind of specific. It doesn't have to be, sometimes it can be a coincidence, but you know, sometimes something just draws our attention and we pull the thread, try to explore it until we find the solution. Sometimes we go the wrong way, sometimes it's the correct one. So we would need to copy the data to paste it in the CyberChef. So you can go here and you go copy as hex stream. Okay, so here on the data in the left window, right click, copy as hex stream, and let's put it in the CyberChef. And let's say from hexdump, or sorry, from hex. And we get some nonsense. This really doesn't help us much. We again see 2291. That much we figured out already, but the rest of the stuff is means really nothing to us. But we notice this 18F8B, so let's try to maybe remove the part before this 1F8B and see what happens. You literally sometimes have to try stuff out. And suddenly something appeared in the CyberChef. This is a magic wand. So let's click it and see what the CyberChef will do. Okay, does anything here look familiar? Now we have a bit of a better situation. Yes? Yes, of course. Yeah, sorry. I don't know if the cyber... Is this any better? Yeah. Of course. So let me also move it like this. I can zoom in even more. Okay, so we have -1. Then there is some IP address. Then there is some stuff. I don't know what it is. Then there is a reverse DNS and some more stuff. So it looks like a some packet, right? We have the IP address, we have the some data inside, but we still don't know what this -1 is. And that's where we come back to that. Sorry. Yeah, it's here. Question. What is the 1F8B? Nice. Yeah. So, sorry. So once the wait a second. Yeah. So once we remove those first bytes that were actually confirming our hypothesis, that they were saying to us how much data is after. Once we got this 1F8B as the first thing, suddenly CyberChef could recognize what's going on. So why is that? If you... Okay, let me remove this. So what did the CyberChef suggest us to do, or what will it produce? The g-unzip, if you see. So the question is, how does CyberChef know that this is a gzip file? Or the, yeah.
Maybe you want F8B is a signature of that file?
Exactly. Perfect. Which flavor? Strawberry, lemon, orange? Strawberry. Oh, sorry. Close enough. Exactly. So that's what we call magic bytes, and they basically tell us, and like when you want to open a PDF file, the reason why some other app and not the PDF reader, why PDF reader opens, is because of these magic bytes. And you can find a very nice list here of all of them. Yeah, magic numbers. So 1F8B is the magic byte for the G unzip, but it could have been some other file or data.
So just to recap, the magic bytes are a sequence of bytes that are in front of a file. Like when you open a file like this in hexadecimal, you will see these first bytes, and these identify the type format of the file, okay? So in this case, as Maurice was saying, the 1F8B,
yeah.
So this it means that the format is gzip, right?
Yeah, gzip.
Compressor.
Yeah, for example, you see 1F9D is tar, or you can have GIF is GIF. So GIF, my God, GIF is 4749. So the every type of file has its magic bytes, so that we can recognize them by it. So nice. We learned something about this packet that we analyzed. Also, here is the second 1F8B. So if we remove the first part, we will get rid of this -1. So this is, and if you count this, you will see it's 22 of bytes here. So that was that 22 plus and then 91 for the rest. And you see it still recognizes it because it begins with the 1F8B, or our magic byte. Okay, so yeah, please stop me if I'm too fast.
Quick question regarding the magic bytes.
Mm-hmm.
Would that also be a way how to bypass some filtering with like uploading the files in web applications?
Yeah, I guess so. You could use them there as well. Yeah. So we analyze this first packet, but look, there's an entire communication going on. So let's maybe check all the packets that contain data, because the other packets are not interesting to us if there's no data. So if you want to add to your filter to also include just the packets with the data, you can click on the field like this, like data here, and then apply as filter, and then end selected. And you should get a filter like this. So we have some 194,000 packets with data, which is a lot, of course. And if you look at here, some packets are bigger, and these don't even follow the kind of the same pattern as our first packet. Some are smaller again. What we can, if we scroll a bit, notice here that these smaller packets kind of follow the format of our first packet. So depending of the type of analysis you're doing, we're just now gonna look at these smaller packets, so it's easier and faster for us, so that we don't lose too much time, and so that we can get actually some nice samples and analyze them. Right? So as I said, there's a bunch of these packets. We can't do each one of these, okay, copy it, go to CyberChef, remove some stuff, get the magic wand, translate it. It would take forever, so we need to kind of automate extraction, because of course when you're reversing some stuff, you do a lot of things, step by step, but if you have an opportunity to automate something, use it, because you're gonna need that time for something else. So we can also follow these packets, and as I said, we're just gonna look at these of smaller length, so let's limit ourselves to like 300. Yeah, I think that's a pretty nice length. So you can either copy paste this filter, or you can again click on the length and then add as a filter and data. But either way, let's just extract these smaller ones. Online people, I hope everything is okay with you as well. This is still, you're doing this on your own laptops, so we're gonna move to Dockers and CyberLab in a few minutes. So okay, we have these smaller files. Okay, around 14,000 of them, bit less, so that's good. Still, we wanna automate this. So let's go now in our Dockers, everyone, or CyberLab. You can quit the, if you haven't, the GDB, and let's go to the first example directory. Yes, online people. So we're gonna need this pickup file that you're running on the on your devices. We're gonna be using it now in the Dockers. The CTU students should have it already in this folder, but you online people will need to download it to the CyberLab. So this is the curl command. If for some reason some of the CTU students don't have it, you can do the same command and get this pickup in your Docker. Okay. And now we're gonna use T-Shark, which is kind of a shell Wireshark thingy, to get the data into a log file. So we're gonna apply the same filter, port 8000, we'll look at the packets with the data and the packets that have the length less than or equal to 300. So this might take a few seconds. So is it clear to you the motivation why we are doing this now, why we want to automate stuff, and why we're not looking, I mean, we did the first packet, you know, manually just to show the principle, but now we're gonna see how we can do what the CyberChef did on one packet, basically how we can do it by writing some code and how we can do it automated even for multiple packets at once. So let's see if we have our file. It would seem that we do. Perfect. So again, I'm gonna show you one example just by hand, and then we're gonna, there's a Python script as well, it should be in this directory, that we're gonna run, that's gonna do this for us. But just for you to get a hang of what the code in the Python script does, just gonna do it like this step by step. So we can do it in Python REPL. Okay, so we're gonna open the file we just created called small data log. Okay, and we're gonna read the lines there. Okay, press twice to get here, and now we can just check the first packet, just to see that everything is all right. Yeah, this is the packet we recognize from just a few minutes ago, 2291, 1F8B, and then the rest of the packet, or rest of the data, actually. So we want to extract, because we need this header, because not every packet is going to be 2291. We're going to have different sizes of packets and different sizes of data. So we want to extract these first numbers in order to know how much data we can expect later. So for example, we can this is int, because here we're going to get the bytes, but then we want just the integer. So we, from hex, from the first packet, we get these 22, and we just print it as integer. Right? You can get the entire byte stream. So now we want two things. So part one takes the byte stream, what we have here, and it goes from the 6th byte to 6 plus 22 y. what's gonna be the part 1? So if we go from 6 to 3, 4, 5, 6, it's gonna go from here and then 22 to here. Because we want to separate this part from the data. This is the part that tells us, okay, it's gzip. And then we can, in the same way, get the second part, which goes again from here, and is the data stream that we saw earlier. Okay. And then we're just gonna decompress it now, but we need to import it first. Import gzip, and then okay, if we decompress the part 1, if you remember, the first 22 bytes were that -1 that was in front of the address. You see it here. And we can also unzip the part 2, and we're gonna get that 147.32, again, the IP address, some data, the reverse DNS lookup. So, did everybody do this part? Yes, okay, thank you for confirming. So now we want to do it for the rest of the packets, the 14,000 that we have left. So there's this nice Python script, courtesy of Mari, that we can check. Just briefly, the code does similar thing as we did here. We open the file, we go through the entire byte stream, we calculate 2 parts of each one, and then we print them. But this Python script has some issues. Do you maybe know what's the issue? What could be the issue here? The way it's written, I mean, this is just an example to show you, but well, I mean, we're basically we're basing the way we are extracting this packet. We're basing it on the first packet we saw, but not every packet will necessarily follow the same format. So this is kind of a hard-coded thing, but so some packets might not follow the pattern. So for that case, we have this except. Okay, it's not gzipped, and then we move on. The rest is the same. We calculate, here we have we calculate the offset, the sizes of each part, where the magic bytes are, and then the data, and we find both parts, and then we decompress. Okay, so we can run it and see what we will see. Okay. Is everybody here with their Dockers? Is online people, are you okay? Yeah. If I'm too fast, slow me down. If I'm too slow, also say something. I don't want to bore you to death. So we see here the first packet here that we already saw. But there are some other ones. For example, if we look here, info, method, info again. Does somebody maybe want to say what this might represent? Or if you find some other interesting packets somewhere. Again, we have it here, yeah, info, method, info. Any ideas? Here we have, for example, load, method, load. So we have method info, method load. And remember what the pickup file is, what kind of traffic it is, what was monitored, communication between what and what. We had the Android phone device, and we had the command and control server. So we have this info So method info, method load.
From the internet, we have, guess, a function.
Be function or some commands to the infected device what to do. So yeah, thank you internet. Okay, also if you look here we have this ping, very nice. There is some data here. Look, there are some directories even, but look, there's ping here, and then we see the ping again, and ping again, and ping again. So what could this ping be? And it's, for example, we could have also extracted timestamps, not just the data. So if we would analyze those timestamps and we have ping every once in a while.
Android users should find this very familiar, right? Like you should be looking at this and knowing what is happening. Like
Yeah, it's
the storage,
like mostly
emulated, download, right?
Apple users. But yeah, so ping from time to time, it's basically a way how the server checks if their infected device is still active. It's kind of a health check or heartbeat check, you know, okay, from time to time I'm just gonna ping you to see you're still alive, and then I'm gonna send you some command. That's basically what the command and control servers do, and we're gonna have a pretty nice lecture on that right soon. So you're gonna do some bots and servers and stuff, so it's good to know, okay, you need to check if your bots are alive so you don't talk to an empty space. Okay. And yeah, there's many interesting stuff. Again, trying to get some info or even to get files. So these are the commands. Get some, see, directories. The camera here. It's also a common one. These are also an interesting. If you go a bit deeper into the pickup or this thing we extracted, you're gonna find this. What do you think these numbers are? GPS, yes. And let's check where it will take us. I have the map somewhere here. Just delete this. So we are, I think, in Iceland somewhere. Okay, this was done by the student who was doing the traffic analysis and the thesis, so I think she put it randomly here, but yeah, this is, so you can even find the GPS coordinates there. Okay, how are we time-wise? I think good. Yeah, oh, perfect. So, again, did we manage to do everything? No, we just focused now on these smaller packets. We still don't understand everything that was happening in the communication. Maybe there's even some very nice stuff there, but it's a huge pickup file. It takes a long time to analyze it, but it's possible to separate traffic and timestamps, to look at the bigger packets. We skip that. Even there are some Android APK files, we can reverse that. So there's much more work to be done with this monitored traffic. But just for this example of how to reverse a network, like the first steps and like the beginner's introduction, I think this is a really nice and enough. If you want to learn more, there's a blog. Here it's linked, so you can read it. It's yeah, of course.
So to recap a little bit, as Maurice was saying in this first part, there is a lot of things on reverse engineering, right? In this particular example, remember that we got a pickup that, in this case, we knew what it was, but sometimes you don't. And we identified some suspicious connection that was on port 8000, and then we isolated that, and then we look at the traffics and we saw some hexadecimal content being transferred back and forth, right? And then we took that content in hexadecimal, put it in CyberChef, and we saw that there were some patterns, right? We saw some magic bytes here and there repeating, and from there we tried to identify like what it was. We found that it was compressed. we uncompressed it and we found data, right? So that was so cool. And then we found that we have actually too many packets. So we did some Python scripts to automate and extract all the commands that happen. And with this, we have a text file with all the commands, and we can actually build a story and see what data was stolen from the phone, how much the person was compromised, and we can actually use this to build a report and report it to the victim or to the company or to whoever requested the analysis, right? So this is a specific use case on reverse engineering on pickups, which is not a lot of people do. Sometimes they do, but from this you also have network signatures. You can have a lot of things to defend and protect from this type of malware, right? If you know how it looks like, you can automate the defense, okay? So this is like super important. I hope you enjoyed.
Yes, exactly.
Yeah?
Thank you. And yeah, as Vero mentioned, in real analysis, we would have figured out, okay, this is a rat by analyzing, by looking at, okay, there's some command and control, by literally by looking at these commands. Okay, there's somebody sending commands to, and then we would know what the type of malware is. Here at the beginning, we told you what it is, but in real life practice, you would just have the pickup and then figure out based on this what it is. Okay, I think we can do a break now and see you in 10 minutes. Yeah, thank you. Ready? Okay. I guess we can continue. So now we're gonna get our hands properly dirty because we're gonna do a real binary reversing. So just to recap a little bit so far, we revised the assembly GDB. Then we did the first example of reversing. We reversed a network. We looked at some packets. We figured out it's a rat command and control virus and server communicating with the victim. So we finished with that, and now we're gonna start with something new. We're actually gonna reverse a binary. So we're gonna defuse a bomb. Hopefully we're gonna defuse it, otherwise, well, it's gonna explode. So the goal is to reverse the C-based Linux binary, and we're gonna use IDA here, and we're gonna use disassemblers, decompilers, and debuggers, basically every tool that we can think of, because when you're reversing, nothing is off limits. But maybe here's an interesting question for you, since you know reversing, you can apps that are not really that are supposed to be paid, but you know you can, if you reverse them, you get them for free, either some licensed software or even malware. What do you think is reversing legal or illegal type of activity? We can give you a microphone if you want. Okay, it's for a nice dinosaur. We can talk. Okay, so just to repeat for the online people, so it's the answer is it's legal, but it's not okay to distribute then what you reversed later, right? Or if you find some exploit, not to like attack it and. Oh. Yeah, well, interestingly, it depends on the country. For example, in Czech Republic here, it's perfectly legal to reverse. So if you want some software, you don't want to pay for it, but you think you're skilled enough, just get it and reverse it. They can complain all they want. You're doing nothing illegal. Of course, illegal thing is to distribute a reversed software, but for different reasons. Okay, so a small digression and some fun facts for you to know. And now we actually go into reversing something that could potentially be malware. Okay, now it's not, but you know. So this binary bomb, it's a program. It's basically used to teach students and people reversing. It's gonna, when we run it, it's gonna ask us for 6 different, well, not at once, but 6 different strings one by one, and as we input the correct strings every time, we move to the next stage. If we make a mistake, the bomb explodes. Of course, we don't know what the strings are. That's what we have to figure out. And yeah, basically we have to reverse the application to know what the strings should be. So I hope you all have IDA installed. We made a few announcements because it kind of takes time to do it, so I hope that now you'll all be able to follow. And we can actually start with the bomb binary, okay?
Do you all have IDA?
Yes, yes. Channeling my inner Sebastian. Okay.
If you don't have IDA, try to sit with someone that has IDA, okay?
Yeah.
It's okay if you move, we will not judge you. But it's really important that you actually see what is happening, okay?
Yeah,
and
exactly.
the people online as well, try to, if you didn't get IDA, try to install it. It's free, the free version. All the examples are using the free version features, right?
Yes, it should be working. I tested it. So yeah, since it's gonna start getting progressively more difficult, I'm really gonna try to go slow here so that we all can follow and we're all on the same page. Please stop me at any moment you don't understand something, and off we go. God help us. No. So let's go to the second example directory, and there we have you should have the bomb there. Let's just make the file executable and then run it just to see what happens when we run it. This is not malware, so we can I mean, if you trust me, we can feel free to run it, but if you do this with actual malware, if you want to run it, please do it in some sandboxed environment. Don't do it on environments where you have important stuff to lose. So we run our bomb and we get initial message: welcome to my fiendish little bomb. You have 6 phases with which to blow yourself up. Have a nice day. And it waits for something, so we can try. I know it's always the red wire, right? No, it's not the red one. We exploded. Well, this was disappointing. Okay, so we can analyze the file in many ways. So before we put it into IDA, we can, for example, run the file command to see, okay, it's ELF 64-bit. We see it's executable. Or we can do even strings. Okay, this is all the strings here, but or maybe it's better like this. More. So yeah, we see some function names, some imported functions, some error messages. So basically, any text that it's in the code, we can see it this way. Okay. So now it's time for us to open IDA and load the binary file. So, okay, let me do it with you. I'm gonna close my IDA. Okay, I don't mind. So, just a second. Item. And let's, if you've, yeah, did I tell you to, I apologize if I have not, to download the bomb from the, so the binary and get it on your devices. I'm sorry if I skipped this. So if you all have it on our devices, we can open it. So you would go to new and then you would put a bomb, but I already have it, so I'm just gonna open it directly in IDA. but please let me know if you have some errors there. You should see a window like this, similar, and you go OK when you're on the first window, and I think on the second one as well. Oh, actually, it will be yes on the second one and OK in the first window. So please let me know when you see something like this in your laptops. Okay, we have some here. Others, do you see the graph? Don't be shy, we can troubleshoot some stuff now. We have people to help you if there's some issues. So okay, that's one more. Okay, I'm gonna wait just a little bit and to give the online people time as well. So for those of you who have managed to run IDA and see the graph, maybe you can try to press F5 in order to generate pseudocode from it. And then if that doesn't work, it might first give you some window. Just click OK on it. So yeah, just want them to run the pump first. Open them in IDA. So can we continue? Do you have the graph in your, or something that looks like this in your devices? Just a simple nod. 2, 3, 4. Okay, I'm gonna take the silence of the majority as the sign that everything's all right. But please stop me if it's not working. Okay. So before we start analyzing, let's just get familiar with IDA a bit. There are some shortcuts that are gonna be useful for you and some windows as well. For examples, other than this graph view that you see now, if you press space on your laptop's devices, you should get assembly like this, and then you return to the graph again by pressing space. So you're basically looking at the same thing. This is just a feature of IDA to present to you this nicely in some boxes. Okay, there's also a hex view if you needed, some imports, exports. Also you can windows there, you can check these sub views. So if you go to view and then open sub views, and then you can look at the disassembly, exports, imports, functions, strings. Like these are basically the strings that we got when we did the strings in our shells. So there are many useful views that we use in the IDA and while disassembling. Okay. Also, yeah, segments. In the document here, you have the shortcuts for these functionalities. But if you want to see all, again, it's view and then open subviews. Okay. This here, functions window, see here, is where you can see all the functions that are used in this code. And for example, we are here in the main function. Another thing for you to know. Okay, now here when we opened our file in IDA, it put us directly into the main function, but it's not always the case. Often it happens that we have to find and recognize main function and then move to it, especially if the code is obfuscated a bit and some anti-reversing protections are enabled. And then you see the functions, phases of the bomb here, some other API calls, stuff. So this is also a useful view. Let me check if I forgot something. Imports, exports, open sub views. Okay, so did you all try while you're in the main function to press F5 and to get the decompiled version to this? Can you get the code from this from the assembly. In case there are some issues, we have a workaround here. You can download this already database that's prepared with the decompiled versions and then open that in IDA instead of the bomb. So if we all have the code, we can take a look, or we can start diffusing the bomb, I guess. Do I need to? Yeah, maybe a bit. So what is happening here? We're in the main function. We see again this push RBX, compare 1 to EDI, jump 0. Basically it's checking if everything's all right, if it's gonna this is the prologue, but this compare does something different. It checks the number of arguments that are passed in the when you start the application. So if you just start your app, it's just gonna go to this welcome to my finished little bomb like we saw before. But you can also pass another argument, which should be a file. If you don't pass it correctly, you will get the usage message. And from that file, if it can't open it, it will let you know. Otherwise, it's again gonna move into our hello welcome screen. This is done so that because there are multiple stages, that we can save the solution of every stage in a file and then pass it as an argument when we call the application, so that we don't have to type every time if we want to solve the stage 6, so that we don't have to type the solutions for the first 5 stages again, and then so you just pass the file. And so that's basically what we saw here. I know this is assembly, I kind of run through this, but this part is not that important. I will do a very deep analysis of the phase 1, literally just in assembly, and there we will go step by step with every of these registers and what is moved where and how, just see how painful it can get. And the phase 1 is the simplest one, and then the rest ones I won't be so bad to torture you with that. But yeah, if you don't, you can also look at the decompiled version and you can see, okay, if the number, because IDA recognizes that, okay, number of arguments is if it's not 2, then it explains how to what is the usage, if it can't open the file, and then it either way gives you the welcome screen. Okay, another thing that's interesting here, once these things are done, we get into this main part where actually the function calls are made to all these phases. But before that, we have this initialize bomb function. Let's just briefly analyze it. We can even do F5 to get this very simple code. Why isn't it? Trying to increase the size. Okay, but it's very simple. It just returns some kind of signal. So signal to, we don't know what it means. Of course, we don't have to know. That's why we use Google and stuff. So if you look in the Linux manual, so the signal, if you go here, down, you see that the signal 2 is sig init. It's basically Control C. So this function explains, or is how the application will behave if somebody does Control C, and then that is passed to the signal handler, and we can even open that function by, you move through these windows just by double click or enter on you mark the function and you double click. Okay. So basically, if you do Control C, you get this message. So you think you can stop the bomb with Control C. Well, okay, and it exits. I don't know if it's not diffused, but it's stopped. We can even try it. So if we do Control C, okay, there are some sleeps and waits, but it's basically what happens. I guess it's some kind of a joke of the developers, nothing special. It's not a solution to the problem. Okay, so let's start reversing. So to go back, you press Escape button. So if you, for example, go into a function by double-clicking, to go back, you press the Escape, and you're back on the window from which you came. So we know how the bomb looks like, what it does. Now we just have to figure out what inputs we need in order to defuse it. So I think we can start and go into phase 1. Okay. Are we there? Everybody? So far, so good. Okay. Internet perfect. Thank you. So here we see a very simple graph. Not much is going on here. We see sub RSP 8. So we are making a room in stack for the variables, and then some string is put into the RSI register, and then some function is called that is called strings not equal. So, small disclaimer, this example, we're gonna go through this assembly. We're not gonna look at the decompiled versions, just to see how the process of reversing something can be long and not so straightforward, especially mainly because in a lot of situations you won't be able to use the decompiler to get the code nicely. You will have to figure out everything from the disassembler, because the creator of the app or malware will put some obfuscations so that these softwares like IDA or Ghidra won't be able to solve them and to generate the code for you. So you will have to read the assembly slowly in order to understand how to remove the obfuscation so that you can do something else. So we can follow this function, strings not equal, and of course, based on the name of the function, we can assume that it's gonna compare if two strings or multiple strings are equal. But maybe, just maybe, the creator of this made some trick and it actually doesn't check if they are equal, but wants the strings to be of different size. So he wants to trick us with the name of the function. We'll see if that's the case. So again, we have here push, 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 R12, RBX, RBP, RBX, the standard prologue. I told you the opposite thing, the pops are done in the epilogue at the end. So we recognize our prologue and epilogue, so we just need to now figure out what's happening in between, and that's the fun part. So we move RDI to RBX, RSI to RBP. So at the beginning, roughly, before the break, I was talking about some types of registers. So why are we moving these registers now into these, and we're not changing any values or anything? What does this mean? What's so special about RDI and RSI? They're not special. All registers are equal. Well, so it's the case of those non-volatile registers that we have to preserve their value. So we copy them here. And then we see a call to the string length function. Based on the name, we can assume, okay, we are here checking the length of the string. Okay, I won't go too deep because we don't have that much time, but yes, that's basically what the function does. But what string will we check for here? Well, that's why we have these registers before we pass them to the function. But what is their contents? So if you notice, we have two string length calls. So what will be written in these strings? From what we see here, we don't know, because the values of these registers were passed to this function. They were put there some time before. So okay, let's go back. Let's see what was happening before the function call. Okay, there was this LEA, and we put some string into the RSI register. Okay, and that register is passed to this function. And we see here that we move the contents of RSI to RBP. So the RSI register is going to, if you double click on this name of the string, you're gonna get the whole one. So we are like 99% sure now that the RSI register contains this "I'm just a renegade hockey mom" string. Okay. But we still have this other, so that's now moved to RBP, but we still have this RBX register. What's that? Because we have two string lengths. One, okay, string length is gonna check the string length of the string that's already in the memory of the application, but what's this other string length? Any ideas? We don't have to know the answer specifically. Now we can have an idea. What would we want to measure as well here? Where could we get the other string to? From the input, exactly, thank you. It's basically, if you backtrack even before the phase1 function, you can notice this call to a readLine function that basically waits for the user input. That's when we start the application. And that input, again, return value register, RAX, and we move it into RDI, and in strings not equal RDI, we put that value in RBX. So that's basically that. We know what we have in RBX. We have what was our input. In RBP, we have the string in the application. Perfect. We check their lengths. We save them, again, EAX, the 32-bit version of the RAX register. We save that value in this R12 register. The EAX from the second one we put into EDX register, and we put one in EAX. We still don't know why, but we'll find out soon. And we compare what's in this register to R12D to this, well, no, sorry. Yeah, we compare what's in R12D to what's in EDX. And what do these registers contain? What should be the values of these registers? We don't need the exact values, just what's there. What would a string length function return? What do you expect it to return? If somebody tells you, okay, this function is measuring the length of a string, what would you expect as a output? Number, yeah, the length of a string. It's very simple. So we have the length of the first string, the length of the second string, and we compare them. And what does it say here? Jump if not 0. So if they are not of the same length, we're gonna jump out and then the bomb is gonna explode. So we need them to be equal. Okay, so far so good. How many of you are lost? How many of you are not lost? So a lot of you is in some limbo in between of being lost and not lost, I guess. Yeah, I will. So far, we started to defuse a bomb. We started with the phase 1. We figured out that before phase 1 function is called, we need our input to it, and that value is passed into the phase 1 function. The phase 1 function calls another function which checks if two strings are equal. One string is gonna be our string which we put into the app. The other one is gonna be this one, I'm just a renegade hockey mom. And then we we are trying to figure out what this function exactly does. By the name, we can maybe assume it's comparing if the two strings are equal, but it might be a trick. Maybe they're expected. Maybe now we're gonna see that it's comparing if the other is the first string but moved by 4 characters or something. Maybe some cipher can be in question. We don't know. Of course, we're gonna see at the end that it's just the plain string, but our assumptions can be wrong sometimes. So what I'm doing is to show you on a very, very simple example how to do this step by step. So once, if the two strings have the equal lengths, we need to then check what happens next. So we're gonna analyze these boxes here. We're gonna take the first byte of our string, and we're gonna check if it's a null byte. If it is, we're just gonna leave the function and that's it. But if it's not, we need to do some analysis. And if you look at here nicely, you see this loop. It's looping. So we can assume that some checking of something is going there because it's a loop. It's literally a drawing of a loop. Okay. So what do we compare? We compare here the DL, if you remember the lower 8 bits, to whatever is here. If it's not the same, if it's not 0, we jump, and if they are the same, the compare is gonna return 0. If they are the same, we add 1 to RAX, probably a counter. We can make that assumption now. We move the pointer of the string to the next character, and we test if it's a null character. If not, we check the next, and basically we're comparing it letter by letter. And here is the comparison that's being done. And okay, now just to show if our idea is okay, we can even check briefly the decompiled version, and that's basically what we see. First, if the lengths are the same, that's the first check. Then we check if the string is the null string, and then we check character by character in the while loop if the characters are the same. Luckily, there's no obfuscations, no encryption, anything here.
How do you get to the compiled
to do the compile? It's F5.
Oh.
Yeah. If in case it's not working, we have instructions in the document how to. We have another version of the bomb that should be working, and that should have so F5 on your. And it's gonna run until. So if it happens that these are not. And we see here that that these are not equal, it will jump to here, and here we will set the EAX or RAX, the return value, to 1. Otherwise, if we go through the entire strings and we get they are both null characters, we're gonna end up in this box, you see, and there we're gonna set the return value to 0. So basically it's a bit of opposite. If they are the same, we're gonna have 0 returned. If they are different, we're gonna have 1 returned. And if we go one step back, we have this nice test EAX that basically it's and then after it the jump if not 0, and the jump takes us to the explode bomb function. So we don't want to go there, we don't want to jump, which means that we want the value of this test to be 0, which means that EAX needs to be 0. So we want to end up in this box here where we set the EAX to 0. And then this is just the standard epilogue. We pop the stuff off the stack. So this is step by step how you can look at the assembly. Of course, we could have gone deep into this function as well. There's again a loop here. It's always nice to analyze loops and switch cases. We will see one later. But yeah, even without this very tiresome analysis, we could have just made an assumption, okay, this is the solution to the first phase, and input it here and solve it. But maybe it's not a solution, I don't know. We have to try it to see, to find out. So sorry, I went too far. So let's copy it and let's run our bomb and let's see if we did the right job. Do I need to repeat something? Is anything clear? I know it's a lot. It's
Do they get candies if they say yes?
well, I'm thinking about implementing that practice, like just any feedback of I'm still alive will be appreciated. So let's run the bomb and let's try the first string, and yeah, it's diffused. Yeah, it's here. Okay.
I mean, how awesome is that? You didn't die. You didn't explode, right? Unfortunately, there are more stages. So.
Yeah. So, who has gotten the solution? Have you put it in your system? Did you diffuse the first stage? Well, then, nice job. Congratulations. Quick trivia, TV show reference. Does anybody know? Ah, you're too young. I mean, so am I, but okay. So yeah, that's the correct solution. If somebody on the internet knows, please write it. So nice. And also, the internet, here's something for you. I guess it's time for the daily password. So it's spam jam this week. So I'm gonna leave it here for a few moments, and then we're gonna continue with the class. Spam jam. Okay, 5, 4, 3, 2, 1. And that's it. Okay, so the rest of the stages, we're not gonna go through the assembly. We're gonna try to figure out them from the decompiled versions. It's still gonna get a bit tricky at some moments, so there's no need to if you want, you can do it for yourself when you get home, analyze it slowly, practice assembly, and lose a bit of your eyesight. So just for to make it easier for us ourselves later, let's just put it into a txt file. So the next time we can run the bomb, or wait, maybe I already had it. I just want to remove it in case I already had it, so I don't make complications later on. Okay, and just to show you, if we now run it and pass this as an argument, we're gonna get automatically the phase 1 diffused. Okay. So don't worry, you'll be doing something similar for the assignment. Yeah, well, I should have said it earlier, probably. Okay, so we're gonna continue with the phase 2, I guess. Don't worry, it shouldn't be too hard, especially when you look at the decompiler. So the procedure is there, standard. Again, it waits for a read line. We put something there, it passes it to the function. We're not gonna do it like this. We're gonna press F5 and we're gonna get the code. Let's see if I can. Okay. So does everybody have the code in their laptops? Can you see it? So let's see what's going on here. First thing, okay, there are some variable stuff. The first thing that kind of makes sense to us that we can read normally is, I guess, this read 6 numbers. Okay, so it probably does what it says, but let's check it. Okay, so we have a function, and what's going on here? Scanf. Can somebody say what's... Yeah, we were reading 6 integers. Thank you. Lemon, strawberry, orange. Nice. Okay, so we're basically scanf. We're reading 6 integers, and we're storing them into this array. See, and it's always moved by 4 bytes. And there's another check here. It says if it's less than or equal to 5, the bomb is gonna explode. So if we input more than 6 integers based on this, nothing should happen, but if we have less, it will explode. Okay, let's go one step back. So we know what read 6 numbers does. We have our numbers, and then they are stored in the V3, because you can see here that V3 is an array. We have, for some reason, IDA doesn't recognize that array is of size 6, but it puts 5 and then 1 more. But that's due to the way IDA works. It's we need to input, based on what we saw now, 6 numbers. And what does this check say? Because we have our numbers here, right, in the array. If the first one is not 1, we explode the bomb. So we know how our array starts. We start with 1. And this is where all the money is, what's happening in this function. So does anybody care to... It's simple, it's not assembly, it's just code, so yeah.
So we check the first number if it's 1, and then we check the next number if it's multiplicated by 2.
Okay.
So it should be 2, and then 4, then 8, and this array should contain this second
Yes.
sequence.
Perfect, that's it. Thank you. I guess you can come later, or if you trust me to throw it, but I'm gonna hit someone probably. So yeah, just to repeat for the people online, we are checking, okay, if the first number is 1, and then we check if the next number is twice as big, then we move the pointer of the array, check if the next number is twice as big, so we will eventually have 1, 2, 4, 8, 16, 32. I think that's 6 numbers. And then we leave the function, and that should be it. So let's try it. Let's run our bomb. So 1, 2, 4, 8, 16, 32. That's number 2. Okay. Good guess. Let me know when you get there. You can also put it in the input txt in order to... Yep. Okay, boom. So, do we all have the 2 stages solved? Yeah, nice. I guess we can continue with the 3rd one. Okay, phase 3. This is where it starts to get fun. So, let's look at the assembly briefly. I'm gonna now zoom out a bit so that you can see how it looks. But basically what you're looking at here, this very nice graph structure, this is how a switch case looks represented in IDA once it's disassembled. So you can see here the jump tables and some conditions, and then what happens if this, if that. But let's not analyze it like this. Again, we press F5 and we're gonna look at the code. So again, we start with some scanf, but this time we we are expected to input two values. So if we put one or less, the bomb is gonna explode. That's basically this condition here, and they are gonna be stored in V11, V12. We can, to show you another thing in IDA, you can rename these things. So if you press N, you're gonna get a window like this, and you can rename a variable, because sometimes you're gonna have a huge code, you can't remember what V11 is or V16 or some random stuff. So you can say number 1, and again N, number 2. Okay. So what happens here in our switch case? We are looking at the value of number 1, and then if 1 is 0, then we do something to V2, whatever V2 is, we still don't know, and then we go to label 5. Then we do something to V3, and we go to label 6. Then we do something to etc. Or if our first number we input is 1, then we do this. If we input it 2, and it goes all the way to 7. And then there's the default case. So there's some like 8 numbers from 0 to 7 which we can potentially input, otherwise the bomb is gonna explode. And what else do we know? We know that if number 1 is greater than 5, or if number 2 is not equal to whatever V9 is, the bomb is gonna explode. Okay? So number 1 can be 0, 1, 2, 3, 4. We still don't know. So just arbitrarily, we can try, just like when you're debugging something, take a random value and see, go through code, see what will happen. So let's say we take 4, we go to case 4, it's here. So what's happening? V5 is set to 0. Okay. V6 is equal to V5 plus 126. So that should be 126. Then we go to label 9. There it says that V7 is V6 minus 126, so it should be 0. Then we go to label 10. It's again 126 because V7 is 0. And then there's a break. And we say that V9 is V8 minus 126. So it was 126, right? So it's V9 is 0. So number 2 should be 0. So if our number 1 is 4, number 2 is 0. And you can do it this way once you have a simple task, like here, a simple switch case. But sometimes it can get really complicated. So I want to show you a different way and some different tools that you can use to actually figure this stuff out. Okay, so did you follow so far? Do you know at least roughly what the function is doing, what it's checking, what it's expecting from us? So there was that first condition that we input 2 numbers, and then we saw at the end that they have to be less than 5. Yeah, the first number has to be less than 5, and then we have to figure out what the second number is. So in order not to, when we have a bigger switch cases, not to do this manually or with pen and paper, we can actually use GDB. That's why, you know, debugging always helps. So let's put 4 and 100 into our bomb input, and let's run GDB with it. We put 100 arbitrarily. We don't know what the value of the second number should be, so we guess it and we see how in the debugger it will behave. Okay, so that's the choice behind the 100, and the 4 was again chosen randomly before. There wasn't a special reason. So we run the GDB with bomb 64, okay, and we put a breakpoint at phase 3. Are we there? Am I too fast? Okay. So now that we have a breakpoint, we can run the binary. and we stopped somewhere. Okay. We can even disassemble it to take a look at exactly where we are, what's going on. I'm just gonna give me a second. Okay, perfect. Just wanna run it again. So just gonna do this here, right? And so let's put a breakpoint at phase 3, and then we can run it with our input. Okay, perfect. So, and we can even disassemble it to see what exactly is going on. So we are in the function. Basically, this is a view we can also see in IDA if we go to from the graph and press space. But why am I disassembling it here? Because we want to figure out what the value of the second our second input should be. So there's, if you remember, we have those two comparisons. The first one is checking if the first one, if our first input is greater than 5, and the second one is checking if our input is equal to whatever that variable should be. So we should stop somewhere there. So let's stop before, let's put a breakpoint before this first comparison. So find the comparisons in your disassembly. So there should be one comparison that's comparing if the value is greater than 5, there's this jump greater, and then there is another comparison jump equal, and copy the address of the command before it, okay? And we're gonna put a breakpoint there. Breakpoint 2. Okay, and we're gonna press C for continue, so it's just gonna go to this breakpoint. Okay. And here we see the stack. This is the view of the stack. Here we see the values of the registers, RAX, RBX, RCX, etc. So let's press next instruction to get to this comparison. Let's see if something changed here. So we're gonna compare if whatever is at RSP to 5. So let's try to see beforehand what's there. RSP. So the value is 4 because our input was 4. Okay. If we check for the RSP plus 04, we're gonna see 64, which is hex for 100. So these are our inputs. Okay. But we want to know what is in this EAX actually. But we need to get to there. So let's do again next instruction. The jump is not going to be taken, which is good because 4 is less than 5. Next instruction. And we compare something here. So let's check what's in in our ESP. Sorry, in the EAX. So we see here in RAX it's 0 if you scroll a bit up, and EAX is just, RAX is 64-bit, again the EAX is 32-bit. There's no need to store 64 zeros, so they just keep it here as 32. So our EAX has value of 0. Maybe we can even check it like I need a dollar. Yeah, it's 0. So we have the wrong value in our second value, in our second variable. So as I showed in the example before, or in the first class, we can change the value. So let's get the address of what's at RSP plus 4. Yeah, so we have our 100, and this is our address. So we do set star the address equal to 0 or just 0 should work. And then if we do NE, we see that, okay, jump is taken. If we press continue, yeah, we get the halfway there, which means we solved it correctly. So if we exit, what's it? Input, so we change this to 0. And if we run our bomb again with this, we should get a very nice message that we are halfway done. Okay, keep going. So is everybody here? Did anybody get stuck? Did anybody not understand something?
Why are we doing this?
Because some people want us to. No, come on, it's fun. Okay, it goes a bit slow now, but it's basically, if you want to analyze the code, it's hard, but it's very rewarding once you figure out what's the solution. Okay, so do you all have the 3 phases solved? No big questions? Good. And I think it's time for a break for all of us to rest your brains a bit, little gray cells, and then I'll see you back in 10 minutes for the hardest 3 phases. No, and if there are some questions, please ask at the beginning of the next one. Yes, we can continue. Okay, there's still 1 or 2 of you missing. Maybe not. Okay, before we move to the phase 4, thank you. There was someone online who knows the reference. It's Twin Peaks. If you haven't seen it, it's amazing. It's a bit like this class. You will be watching it and you won't have a faintest idea what's going on. But it's a brilliant show, directed by David Lynch. So if you want something fun and interesting, really interesting to watch, that there's a recommendation for you. Okay, so I guess I can continue with the phase 4. Are we ready? Do we still remember the first 3 phases, what we did, how it looked like? So let's move on. So phase 4, just gonna go back from here. We can double click on it and we open the window. We're too tired for the disassembly. Let's just look at the code and see what's going on here. Okay, so we have again some scanf. We are again expecting 2 values. And there are some now other interesting things. The bomb is gonna explode if we don't input 2 values, if it's more or less. But also if the first value, which is here v2, so I'm just gonna rename it to number 1 and number 2. 1, 2. Yeah.
So the process of what Maurice is doing of renaming variables is so common and so useful, right? Because you cannot pretend to or try to keep everything in your memory. Our
Yeah.
memories have limitations, right? So as you are understanding the code, this renaming and making it more understandable, the code, it will help you kind of recap, right? Like, oh, what did I learn so far? Where I am? What is this function? And then you can quickly go and check. So this is fundamental, right?
Yeah, because you won't be able always to solve it in a day, and then you're gonna come back tomorrow and you're gonna forget what was what. So you need a bit of the code is unreadable, so make it readable for yourself. That's the basically idea, because you're gonna thank yourself later. Okay, so we have a check that we input two numbers, and this check here is that number 1, if it's greater than E, the bomb's gonna explode. So if you're not sure what it is, you can press letter H and it's gonna convert hex into like decimal, and so that's 14. So if it's 15 and more, we explode. So we know roughly the values we expect. We still have to figure them out somehow. So let's look at the next condition. We are calling some function called func4. And we pass to it our first input value, 0 and 14. And that's the first check. And whatever the function func4 returns should be different than 10. Are we okay with this? And there is another OR which says if the number 2 is different than 10, we explode. So we know one number. Perfect. We know that number 2 is 10. We still have to figure out the first number. And we get the first number by looking at this function, because the return of this function needs to be 10. So let's follow the function, double click on it, and we get a new window. And what do we see here? Something that every programming student, especially those who are just learning programming, love. We see, okay, we are in function 4, and then we see some conditions, and then we see function 4 again and function 4 again, or as we would say it, recursion. Perfect, thank you. So we have some recursion, and we can try to now take a pen and paper and write steps down, take an arbitrary value, but why waste time when we are programmers and we can write code and we know Python? So we're just gonna rewrite this in Python and get our values that way. I mean, look, the reversing, you have the freedom to do whatever you want that gets you towards the solution. So if you why waste your own time, and why suffer if you can do something very neatly? So no need to pretend that you are too smart, or just, maybe you are, but you don't want to waste your time. So here we have this phase for Python. You should have it in your directories as well. So let's check the code a bit first, and then we're gonna discuss what's going on. So we basically, the pseudocode of the function that we have there, we rewrote it there. We have our standard 3 inputs. And we know that the first one is our number, the second one is 0, the third one is 14. And we check here, okay, there's some division, the first condition, the else, something that returns. And what we added here is what also we know, that the number is less than 15, right? So we are just gonna run this code for all the numbers from 1 to 15, which is not much, so it shouldn't take long. And once we get the result, or the return value, this v310, our code is gonna say, yay, correct input, and we're gonna know what's the value that returned us the correct input. So no need to even analyze this function too much, because we have a way how to get a solution from it. So so let's just run it and see what's the first number we have to input. And it's 3. So let's try our bomb. So we know that the first number is 3, and based on the condition Here we know that the second number, if it's not 10, the bomb is gonna explode. So we need it to be 10. So we do 3, 10. And yeah, this one wasn't as bad, right? I mean, the first one also wouldn't have been, but I decided to torture you with the disassembly, so I'm sorry. Okay, you have this one. Everybody solved. Nice. Congrats. And now we can move to the more serious stuff, the phase 5. But let me just 3, 10 into the, what was it? Okay, just run it to see. Okay. So we go to phase 5. Let's go back, escape. No, this is pseudocode, sorry. Escape, escape, and phase 5. And what do we see here? I mean, again, this first part, we're by now we're pretty much used to it. We see again this scanf. We need 2 values, and we store them into v5 and v6. Again, I'm just gonna rename it so that I don't get lost later. num1, okay, num2. So if it's not 2 values, we explode. So this is an interesting line, the first thing we haven't seen so far. 0f15. So what are we doing here? We are doing our input and yes. Yes, exactly. It's a bitwise AND, so we just want to have the the max number should be 15, and we'll later just then move again this v1 to number 1. So no matter what our input is, even if it's higher than 15, it's just gonna cut it. So we cut ourselves. You have a toy here. Later, I don't want to throw it now. You can pick which one you want. Okay, and now we have another constraint which said if the input value is 15, we go to label 7, which is explode bomb. So okay, we know it can't be 15. So far so good. And this is the main thing we need to analyze basically in this function, that is what's going on here in this do while. So we see we are taking there is some array, and we are moving through that array. But we need to somehow inspect, okay, what's in this array? What are the values? So let's double click on it and follow it here into the memory to see. And if you count here, you will see that there's 15 values here. 16, sorry.
From the internet, if you could make the text bigger.
I was trying to no. There is somewhere, but it's mostly for those graphs, and it's very counterintuitive because they put you a plus. Yeah. So we have some 16 values here. Oh. Yep. And how long will our so v1, we know it can't be 15 at this stage. So we put that v1 is the first item of the array, and then we move it to the next one, and we move also our, you see the, we increase the this variable, which seems to be the counter, so that we are gonna go through all the values. So we can also rename that to counter. Okay, so we are increasing it with every iteration, and we are going for how long? Until the value where the v1 is pointing equals 15. Okay, so if we go take a look at our array back again, 15, we should, or you can disassemble like this, we have it here. So if you want to turn these hex values into decimal, just press H. So these are basically the values in an array going from 0 to 15, and something is happening. Let's go back to our loop. So what is the second condition here that will make the bomb explode? If the second number we input is not equal to v2, and v2 is the sum of these numbers in the array. Okay, so let's try to look at it from a different angle, I guess. We have an array of 16 numbers going from 0 to 15. We get into the loop, and the loop is going, and it's gonna stop when we reach the value 15 here. So once we get to this index in the array, the loop stops. But we need to go 15 times, because if counter at the end is not equal to 15, the bomb is gonna explode. So we have to go through the entire array, and the last index we have to stop at is the one that contains the value 15. So we have to figure out where we start and then how we go. And we see that the next, we move the v1 to be the index of the, so we have the value at the index we are now. So the next index is that value. So if we are at 1, if the value at where we are now is 5, the next index we are going to the index 5 in that array. And if there is a value 2, then we're gonna go to the index 2 in that array. Is that, do you see that in the code? Mm-hmm. Font, yeah. Oh yeah. Okay, now it's bigger. So let me backtrack again, because I know it's a bit. So we have our two numbers, and we have some array here. The first number is something needs to be, it's gonna be less than 15 or equal to, and it less or equal to 15, but it can't be 15. And then we go into our loop. We start with some index. We have a value there. That value is the index of the next value in the array. And we add that value into the sum. We move on to the next one. And we need to go through all of the items in the array. Okay? So we basically, what we have to figure out here is from which index we start, so that we get to 15 at the end. So we want to end here. So we need to figure out what our input needs to be, our first input, because the first input is going to be the starting index of this array. So how can we do this? We need to end up here.
We need to go to like before number, which now is index
So you, okay, just to repeat for the people online. So the colleague is saying we wanna backtrack basically, right? Go from 15. So it's index 0, 1, 2, 3, 4, 5, 6. So we so we need to be there before that here, and then backtrack from there. But that's a correct approach. Eventually, you're gonna get to a solution, and that's it. But it's very easy to make a mistake there. So correct solution, perfect. Thank you. There's another fun approach we can do here. Just look that we are stopping the loop here at 15. So do you maybe have some other idea how we can figure out what should be the starting number? Okay, yeah, one thing is, yes, we can try like we did for every number before, and we're eventually gonna get there. But there's a neat trick here, because, okay, this loop stops after it's bounded, it's gonna end at some point. So what if we were to let it run for a while? So what it happens after it gets to 15? Where is it gonna go next? It's gonna go to the number which is at index 15, right? Because it's always taking the next one. So it's gonna go to 5. But that's also then the first value, right? Because we're gonna start then from the beginning, because we once go through the entire array, we're just gonna start from the beginning. So if the loop were not to stop once we reach 15 but continue, the next number we would end up would be at index 15, which would be 5. And then it would continue, and then we would eventually get to 15. So we can figure out from that, okay, either by backtracking, as you suggested, or by figuring out that we can let the loop run forever, and then just after not stopping at 15, looking at the next number, it's gonna start from the beginning, and the beginning is basically what we need. So the 5 should be the answer. Or we can try to backtrack it now, and eventually we're gonna end up with 5. So are we okay? Did I confuse you completely? Or are you just a little bit confused? Okay, so we know the first value. First value, we say this number 1 should be 5. But what about the number 2? It should be, if it's different than v2, we're gonna explode. And what do we store in v2? How do we create v2? What should be in there? The sum of all the values. So does anybody know the sum here, or is willing to quickly calculate it? And I'm gonna prepare for the input, so it should be 5 and whatever you tell me here, 120. And you killed us all. Okay. Now, but it's very close. No, it's just a little trick here that we have to be careful for. But thank you for actually interacting. If you notice here, this nice thingy, it's ++ counter, and after that, we first move the array, the index, and then we add it to the sum. So the first one won't be in the sum, because the 5 will never be added to this 0 here. We will first move it to R, and then we will add what is there. So we will actually, the solution would be 115. So 5, 1, 1, 5. And yeah, nice. Congratulations. One more to go. If you haven't given up so far, kudos to you. You get another one. Okay, you could have also done this with the GDB. You could have put 5 and 120 and see what is going on. Sometimes when you get stuck, you just turn on the debugger. You have your assumption of the value, and you read in the registers what's it compared to, and then you just fix your mistake if you've made one. Okay? So we could have used the GDB here as well. But it's more or less the same like in the two examples ago, where we would look for the registers, the value, and then change the value of our wrong assumption to the right value. There's some online question.
No. Anyone has any questions apart from the example, like reversing so far, what we did? Like, why are we doing this again? Yeah,
Well,
internet. This is nice because when the bomb explodes, we are not dying, so we
yeah,
can
exactly.
try again, right?
So why are we doing it? Imagine that it's a real bomb, so if you don't defuse it, you'll... I think last year we were saving kittens or something, yeah. Now I don't have kittens, I just have thumbs up for you when you do it. But yeah, I mean, why are we doing this? You know, a lot of antivirus companies, and they have their teams of reverse engineers because they are always analyzing new malware and then enhancing their antivirus detections and fixes with that. And then, you know, you get a new malware, then they analyze it, and you know, it's hard. The thing with reverse engineering, it's at the beginning it's really hard and confusing. There's a really steep learning curve, but once you get enough experience with it, you'll be more familiar with it. But yeah, you can say if you...
Yeah, and also remember that in cybersecurity we have a very special cat and mouse game, right? So you have an antivirus, which is an executable that you run on your machine, and the bad guys, let's call them, they also can have it and install it, and they can actually reverse engineer your program and see how to evade it. And then they are doing malware, evading your antivirus, and then you are reversing their malware to see how they are evading your antivirus. So it's always trying to get an edge, right? Like trying to see how to bypass something, how things work, how can we do something to stop more malware instead of just one sample. So you're kind of reversing, but also building your knowledge and try to see how to make things more secure, right?
So, if you really think you might be into this or still trying to figure out, there's a really good course at FIT, but it's just the reverse, you know, engineering. So if you're like studying cybersecurity here or something, it's a really good thing for like your specialization and stuff. You do much harder stuff there, and mostly without the compiler, because you know you have to go step by step, and but you know, you cry a bit, but then you're happy when you solve it. Yeah, and the exams and cracking passwords, finding passwords. You know, like there are like similar CTFDs, but you just have to find a password hidden somewhere in the application, which is not only hidden but also encrypted. So you have to figure out the encryption, and all just by reading the assembly. So. No, truly great course, and the professor is really good. So if you want to look deeper into this, like we're trying to put here in 3 hours, even less, but we can only just explain you the concept and maybe either kill your interest in this or enhance it. There's no in between with reverse engineering. You either love it or you hate it. You can't really feel indifferent to it. But yeah. Okay, so that was a brief intermission to rest our brains again, because I know we're all tired. It's been a long week. There were midterms and stuff before, so we're going slowly. This is the last phase, so if we do this successfully, then you can go home, I guess. So, are we ready? Can we do the last one and then get a lot of thumbs up? Okay. So, phase 6. phase 6. Here we are. You're not gonna... You see it's a big one. There's a lot of stuff going on here. No, okay, it's not too big, but you know, we can look at it briefly and then be thankful that we have this F5 button to actually look at the something that looks like code. Okay, so what do we have here? We have some array that's interesting, some values, and then some stuff that is happening here. So I'm just gonna rename this array so it's easier for us later. We can call it input array, because as you see, we are this first part. The function is again called read 6 numbers, so we are expected to again input some 6 numbers into our array. So there are some other conditions that will make the bomb explode or not explode. The first one says basically what the function does. Well, no, sorry. This one says if the value of, and it checks it for every number, if the value -1 is greater than 5, then we explode, so the maximum value is 6. So we have 6 numbers, maximum value is 6. And yeah, if we we input 6 numbers, it's gonna break when the counter gets to 6. And then there is this do while, which is nice. And what does it say? Can we maybe try to look at it a bit? So we have our 6 values. Here we have our pointer to now one of those. And we are checking our input array at the V3. And it's gonna explode. Yeah, okay, we're all tired, I understand it. Basically, if we get number that is, if we get 2 same numbers, we're gonna explode. So we have array of 6 numbers, all have to be different, so we're just looking the permutation of from 1 to 6 of that array. Okay? So we need to figure out in what order to input our numbers. And then we get here, we're going to 6, we have our input array, and we have this node 1. And we don't know what it is. So when we don't know what something is, we follow it. And I'm just gonna decrease the font a bit. Okay, so we have some node 1, node 2, node 3, node 4, node 5. And there are some values here. We don't know what they mean, but we can try to understand them. So here we have prepared what these dB, what does dB mean, and so dB is byte, and then you see here multiple bytes, so you can combine multiple bytes into a word to a double word or quad word, and to do this, press the D for data on your keyboard. So D, and also at this too we can do it D. Okay, and we can do it for all the nodes. Okay, is this working for everyone? So we see that our node has some kind of tree information here, some value, some other value, and something that looks like a pointer to another node. So if you think about it, we can represent these nodes as this, and I'm sure this is something you've all seen a bunch of times in your programming classes, and we might use this, for example, in a data structure called linked list. So yes, no. So as we assumed from what we saw here, we have the value, we have the ID of the node, and the pointer to the next node. But what is happening here? Why is IDA not recognizing this as a structure? We don't know. Sometimes, you know, these tools are not perfect. They can't recognize everything. That's why we need us humans to actually do this stuff. But we can help IDA actually. So we figured out with our analysis that this is a structure. So let's create a structure and then tell it to IDA, this is a structure. So we go to the structures window. I have so many stuff here. Yeah. And in the structures window, you can either press insert or should be, yeah. Yes. The view structures, yes, of course. So if you don't see it in your like these, you can go to view, open subviews, and then you can find it. Should be in structures or below. Yeah, Shift F9 or just in the window. So view, open subviews, and if you don't see it there, try Shift F9. Nope. Okay, that's interesting. Not sure. Okay, let's. I mean, when we're stuck, we ask Google. Not this, I want the submenu. Maybe, but still. You. Okay, open structures window. Structure. Open subviews. If you find it, please say something. F9. Okay. Hmm. Yeah, it's possible, but why would they change such a silly thing? And you see all the other views, right? In the these subviews, you see the strings and functions, and like in your IDAS, it's just the structures are missing for some reason, or hmm? Oh, you have it there. Okay. Yeah, but it shouldn't be because that's subview. Even if you don't have any structure in the code, the subview could be there because you can add a structure. Hmm. Okay, I will try for a. Okay, we have.
So if you can chat
some
us the
time.
version, yeah. Can you put the versions that you have on the matrix?
Yeah, so we can.
Okay.
I don't think you will need it for the assignment, luckily, but
Okay, let's continue.
yeah, this is kind of a special example.
If you
really.
can put the version you have of
Oh,
IDA.
if you go to Windows and then structures, do you see it there? So Windows structures, maybe Alt +8 or something. Ah. Oh yeah, true. Okay. Did you hmm. Okay, so they probably changed something. Okay, good to know for the future reference. I apologize for this, but okay, let's then you will, I guess, look at this. Still, you can have hands-on by interacting with me. So now you have a reason more to actually talk to me. So okay, let's name our struct as node struct, and we say okay. And we want to create it, you know, as it is. So we press D to get this field, and we press D, I think, till we get it to DD, yes. Then we press again, D, and D again. And this one we're gonna go to DQ. Okay. So we should have something like this. I'm just gonna rename these fields to value ID and pointer as they are there. Value ID. Okay. So once we have our structure, what we can do is tell it to IDA, okay, this V7, we want to convert it to struct. So convert to struct, and we choose our node struct that we just created. And suddenly we see these pointers here, and we see what's actually going on here. We also can do this to V8, convert it to struct. Yes. So now we recognize we have a structure in the actually in code. We helped IDA, so IDA helped us because now it's it can recognize which value from the structure are we using, the pointer or the value, or yes. So basically there's a lot of stuff here that doesn't really do much things, but this do while is the next interesting thing going on. So what does it say? If, so what V8, the value, is less than the value of where the V8 is pointing, the bomb is gonna explode. So our values or our pointers need to be in the decreasing order. So we know that our values need to be in the decreasing order. We still don't know how to order our pointers because we don't know which one is pointing there. But we can of course look at the memory like we did before here. So we see that the node 1 has a value 530, node 2 has 450, node 3 has 533, node 4 has 950. Or you can also find this in GDB. We have already done it here. So from the do-while loop, just to recap, we figured out that our values need to be in a decreasing order because the value of our current structure needs to be less than the value of the structure where our current structure is pointing. And we need to order now our inputs that way so that the values are in the decreasing order. So you have all 6 here and the respective nodes. We know from the beginning of the function we have 6 values and each has to be different. So it's a permutation of from 1 to 6. So which would be the first value that we input? So these are the nodes, these are the respective values here. So what would be the final order of the nodes from 1 to 6, or what would the permutation look like? What's the highest value? They need to go in the decreasing order. Five, 4, okay, that's correct. 5, 4, 3, 1, 6, 2. Okay, I think that should be it. So 5, 4, 5, 4, 3, 1, 6, 2. Well, you deserve it. You managed to go through all of this.
Is the assignment similar?
It's not this difficult, don't worry. But so yeah, nice, good job. Thank you for following. I apologize again. I tried many stuff with the, and I didn't even cross my mind they would throw out the structures. I was worried a bit if they would throw out the decompile window because you know that they're literally selling their product, so if they can cut corners anywhere, you know, they don't give you decompiler. But you had a decompiler working, but for some reason structures didn't work, so I was checking the wrong stuff, but I wouldn't have. I guess the next thing is they will cancel strings and imports. At some point we're just gonna be left with the disassembler and that's it. Not okay. I know it was a lot. I know it's new thing for a lot of you, so it's confusing. But thank you for putting up with it through the end and for even some feedback and interaction. It means a lot. I know that at least somewhat you are following. I mean, with this stage 6 was a special case because you have to recognize and then create structures to use IDA and stuff. The earlier stages are more decent, I would say. You just need to know how to read C-like code, and you can figure it out. And I mean, not to deceive ourselves, we now have ChatGPT. It's kind of pretty decent even with the assembly. So if you get stuck, that's another way you can do it. For like this assignment, we won't ask of you to give us step by step what you did. That might happen in the bonus assignment. There we really need you to be detailed in your explanations. Now you just need to find the flags. So yeah, I know it's a lot, but hopefully it wasn't completely useless. We'll see. Hopefully you learned at least a little bit of something.
So this is an introduction to security, right? So reverse engineering is a big part of that. So we are giving you like a sneak peek of the whole field. Of course, as Mori says, you can you can be years studying this, right? So hopefully this class kind of taught you the basics. And of course, there are many tools out there. This is not about the tools. We use something that help us fulfill our goal, which is walking you through all the series of stages and making you understand like how can you look at the code, understand what is the logic and try to bypass something. Or the same with Wireshark, how you can look at the traffic, extract something, and then find what is hidden. But of course, there are many, many tools, and as Mori says, like AI can do great things, but it's still up to you to kind of understand what the AI is telling you, right? So doing this by hand kind of helps you kind of go to the process, and then you can automate. Yes?
This is really useful now, like for AI, if I provided because I assume that you have tried it. So if like it would do these steps that we did for this like simple assignment.
Well, I don't know if it's gonna do the steps. Like if you give it the decompiled version, you know, that C-like code, it's gonna tell you very nicely what the code is doing. If you give it the assembly, it still can tell you what it's doing. Of course, you have to, from that, figure out on yourself what you have to do, you know, with that information. I don't know if they have some like reverse GPTs or something, but I wouldn't be surprised if there actually is. But yeah, I mean, again, tools are nice, but often in the reversing work it happens that they are useless because of some things in the code, and you literally have to go through it like step by step, and that's just the nature of the job. I mean, once you do it, you can improve the tools, but you know, at some point somebody's going to be the first person to do something, and they will have to do it. But again, a lot of these things, just like with everything in life, comes with experience and practice. There are like many binaries online you can download and practice this if you're interested in it. If you're not sure how you feel about it, again, I tell you, take the course, have some fun there at FIT course. It's good. You are really pushed there not to just to do stuff with the assembly and give really detailed explanations of how you got the solution. So you really have to do it, like really have to understand it, but it's worth it. The beginning is the hardest here. Everything else is experience. So are we gonna say something about the assignment or?
Okay. Okay. The assignment will open as usual tonight. We will tell you on Matrix. It has 2 parts. They are connected, so until you don't solve the first one, you cannot solve the second one. All in all, it has 4 points, and you will have to apply what you learn from here. Yay! So, so. The first part is going to incorporate some network component, and the second part, it will be more related to the reverse engineering kind of part. Yeah. And I don't know, should I add something?
Yeah, and this is also for online people. There's a new challenge in Stratos CyberLab, and also for you, so you can play both of them if you want. It has the same skills, but the challenge is different, so you can play both and learn something.
Yeah.
Yep. Thank you.
Yeah, and of course, as usual, leave us the feedback. We really appreciate it. It helps us a lot. Be better the next time we teach. So.
And if you answer some question and you didn't get a candy, there are
Yeah,
still
yeah,
candies
so-
and 3D prints you can take.
So just pick whatever you want from here. And thank you. See you next week. And good luck with the assignment.